This is the first in a series of 4 videos where I will show you synthesis and walk through producing a compound that we want using the various reactions you know on aromatic compounds. So let's consider the compound 1,2-dinitrobenzene. And we'd like to produce this from benzene itself, which is usually the starting material for any synthesis problems in aromatic chemistry. So immediately we see a problem. Because the nitro group is a meta-director, we can't simply nitrate it and then nitrate it again, because if we did, we would end up with the meta isomer. So standard nitration condition, 71% nitric acid, 98% sulfuric acid, that's concentrated nitric and concentrated sulfuric. And if we heat that up, we will put a nitro group on, and if we leave it for a while and heat it more, we'll put a second nitro group there, and then we could in fact heat it even hotter, although usually it takes 100% nitric acid to put the third nitro group to make trinitrobenzene. And that's great if what you want is either 1,3-dinitrobenzene or 1,3,5-trinitrobenzene, but not so good if what you'd like is the ortho or the 1,2-dinitrobenzene. So to get 2 groups in the ortho position to each other like that, we're actually going to need an ortho para-director instead of a meta-director. So we're going to use the fact that we can readily convert a nitro group into an amino group and back using fairly straightforward chemistry. So if we want to reduce the nitro group to the amino group, we can do that with either iron solid and HCl, or the Clemmensen reduction using zinc amalgam and HCl, or we can reduce it with hydrogenation, H2 gas, and a catalyst, often radionickel, at some pressure, perhaps 30 atmospheres, and often in an alcohol solvent. All 3 of those are effective ways to convert nitro groups into amino groups. And we know that we can go back from the aminobenzene to the nitrobenzene using a peroxy acid, CF3CO3H, trifluoroperoxyacetic acid. So we can readily go back and forth from one to the other. Like many syntheses, this one is going to start with mononitration. So the first thing we're going to want to do is make nitrobenzene using concentrated nitric acid and concentrated sulfuric acid. And if we do that under relatively mild conditions, we'll end up with a good yield of the mononitrated product. We're then going to reduce this using one of the 3 sets of conditions. Let's use the Clemmensen reduction, zinc amalgam, and HCl. That's the Clemmensen reduction. And that way we can make aminobenzene, which has the common name amine, and is the third of a large number of different dyes called amylin dyes. So now we have the aminobenzene, and you would think that all you would have to do is nitrate this to put a nitro group in the ortho position. But the problem you face is this is an inductively electron withdrawing group, and that is going to deactivate the ortho positions relative to the para positions and leave the para position as the more likely position for substitution. The other catch is that both the nitration and the sulfonation reactions go under strongly acidic conditions. And if you're working under strongly acidic conditions, like H2SO4, concentrated with FO3 gas, you're going to protonate that. It's a good base. You're not going to get away with not protonating that amine, and this is now a meta-director. Because it's inductively even more electron withdrawing than the NH2 group was, and it no longer has the lone pair that will serve as the ortho-para director. So if we're going to accomplish putting a substituent there in the 2 position or the ortho position, we're going to have to protect the 4 position, which we will do as a sulfonic acid because that's a reversible reaction. But we're also going to have to protect the NH2 group so that we don't get this protonation. So protecting group chemistry is often important in synthesis problems in general, and also specifically on aromatic rings, in order to prevent unwanted side reactions. So the question is, how do we protect that NH2 group? What we want is we want to retain the lone pair so that we can still have the resonance electron donating effect that makes it an ortho-para director, but we would like to make that lone pair less reactive, less basic, so that it won't get protonated under the strongly acidic conditions for sulfonation. And the way to accomplish that is to convert the amine into an amine, because then that lone pair will be stabilized by donation to the adjacent carbonyl group. So we're going to want to convert that into the amide, and the way to do that is to use an acid chloride, like acetyl chloride, which can then get attacked by the nitrogen lone pair and convert that into acetanilide, which is actually the compound that you would be making in the last lab of the semester, although I believe in the last lab of the semester we were going to use acetic anhydride rather than acetyl chloride. The reaction is very similar, acetanilide. Now, this lone pair of electrons is coordinating in a minor resonance structure with the carbonyl group, which makes it significantly less basic, but it's still there, able to donate in as a resonance electron donor to make this an ortho-para directing group. Amides are ortho-para directing. They're less activating than amines, but they're still activating substituents overall. That group can be readily taken back off by base catalyzed hydrolysis. So KOH in water and heat will convert the amide back to the free amine, so we'll be able to take that back off when we're ready to take it back off in the end. You'll notice that we have a chloride here. HCl is also generated in this reaction. It could be quenched with another equivalent of aniline, but if your amine is expensive, if you're working with a more expensive aromatic, you usually don't want that. So generally, you put in a tertiary amine as a sink to react with the excess HCl. That's often triethylamine, TEA, or diisopropyl ethylamine, DIEA, which is even more sterically hindered, and is also referred to as Houdini's space, because organic chemists never miss an opportunity to name something after each other. So diisopropyl ethylamine simply looks like that. It's kind of the granddaddy of sterically hindered bases, so it's not going to do anything but react with the HCl, or quench the HCl that's generated. Now that we have our protecting group in place, we're going to be able to react that under sulfonation conditions with fuming sulfuric acid. SO3 gas dissolved in H2SO4. So there isn't really any water left because it reacts with the excess SO3 gas. This is what we call fuming sulfuric acid. Because there's always some SO3 gas escaping from solution, that will put a sulfonic acid group here in the para position, and thus protect that para position from reacting in ways that we don't want it to. So we now have a protecting group on the nitrogen, and we have a protecting group at the 4 position on the benzene ring. The next step is going to be to put another nitro group in, but now the nitro group will go where we want it to. It'll go in that ortho position. There are 2 ortho positions. It's a symmetrical molecule, so they're equivalent. So we can simply continue this synthesis by doing another nitration, 71% nitric acid, 98% sulfuric acid. We actually have both an ortho para director and a meta director. This would like to put it in the meta position, which is position 2. This would like to put it in the ortho position, which is position 2. So in this particular case, we actually have 2 functional groups on the molecule that are both trying to direct to the same position, ortho to the amide group. So we will now have the second nitrogen attached to the ring in the position we want it. We have our sulfonic acid group. Now it's time to deprotect. We want to take the sulfonic acid group off. And we can do that with dilute sulfuric acid in water. That's going to do exactly the reverse of the reaction here. We had SO3. It will generate SO3 gas. The SO3 gas will react with the water to form H2SO4, and that'll drive the equilibrium forward and deprotect that 4 position. Have our NO2 group. Now we're going to deprotect the acetyl group. So reaction water and heat. Like a saponification reaction, but on an amine instead of on an ester. Acetic acid being the other product of that, or acetate ion in the case of sodium hydroxide. And then the only thing we need to do now is convert this NH2 group back to a nitro group by reacting this with trifluoroperoxyacetic acid, usually written as CF3CO3H. You have to be careful to notice that there are 3 oxygens there, which means you have the peroxy acid link. And that's the last step in our synthesis of 1,2-dinitrobenzene, or ortho-dinitrobenzene. So it's more complicated than it looks at first glance because of the need to protect and deprotect. We have multiple steps. Our first step is to nitrate the ring. Our second step is to protect the nitrogen. Our third step, once we have the acetamylate, is to protect the 4' position, or the 4 position rather, with the sulfonic acid group. Then our fourth step, to do the nitration to connect the second CN bond. Then we deprotect. In the 5th step, to take off the sulfonic acid. In the 6th step, to remove the acetyl protecting group. And a 7th step, to oxidize that NH2 group back up to the NO2 group. So if I wanted to have the entire synthesis on board all at once, it would look like this. Starting with benzene, reacting with 71% nitric and 98% sulfuric. To do the nitration in step 1, taking the nitro group up to the NH2 group in step 2 with zinc amalgam and HCl, that's the Clemenson reduction. In step 3, we're going to protect that with acetyl chloride and perhaps Unix base or triethylamine as a HCl sink. Step 4, fuming sulfuric acid. Step 5, nitric acid to do a second nitration. Step 6, removing the sulfonic acid group. Step 7, base catalyzed hydrolysis of the amide. And then step 8, oxidizing the NH2 group back up to the NO2 group. I skipped this step when I was counting before. I forgot about that step, which is why I had said 7 steps before, but it's actually 8. 4 of which are protection and deprotection.